Hello dear students, in this session we are going to discuss about the deadlock avoidance. In the last class we discussed about the deadlock prevention, in which we discussed how to make any one of the conditions not to happen in order to avoid the deadlock. But in this session we are going to study different approach, that is nothing but deadlock avoidance. Students, the problem with the deadlock prevention mechanism is the lower device utilization and the reduced system throughput. Whatever the number of resources, they will be utilized at the lower rate, and the whole system output or the performance will be reduced in the deadlock prevention mechanism. See, to avoid this, we can have the approach of deadlock avoidance, in which this requires each process declare the maximum number of resources each type it need. Given a priori information about the maximum number of resources of each type, they may be requested for each process. It's possible to construct an algorithm that ensures that the system will never enter to a deadlock state. See, this approach is nothing but the deadlock avoidance approach. This avoidance algorithm dynamically examines the resource allocation state to ensure that a circular wait never happens. The resource allocation state is defined by the available and the allocated resources and the maximum demands of the process. This is what the resource allocation state, where we have all these three data or statistics available: the maximum number of available resource available, again of instance, and the allocated resources and the maximum demands of the process. See, let us study about a safe state now. What is a safe state? Safe state is a state in a system if it can allocate the resources to each process in some order and still avoid deadlock. That is called as state law. When a process requests an available resources, system must decide if immediate allocation leaves the system in a safe state. That is very important, because if it cannot leave a safe state, there may be possibility of the deadlock. See how we can, of course, formally define safe state. Safe state is a state, yes, if a system is in safe state if there exists a sequence like P1, P2 up to Pn of all the processes in the system, such that for each Pi the resources that Pi can still request can be satisfied by currently available resources plus the resources held by all the process Pj with j less than I. See, this is what the definition for safe state. See, now what we can think about it again shows different aspects. If Pi resource needs are not immediately available, then Pi can wait until Pj have finished. When Pj is finished, Pi can obtain all the needed resources to complete its task. Of course, and execute allocated resources and terminate. When Pi terminates, the Pi plus 1, it can even now obtain needed resources and it can continue. So that we were in a state where safe state where each process in a fashion is getting all its required resources and getting the works done and finally releasing, so that other process can access the resources. Now we can have different aspects here: a safe state, unsafe state, and deadlock. A safe state is definitely not a deadlock state. It is a deadlock state, free state. Sorry, it is a deadlock free state. But of course, unsafe state may even result in a deadlock. That is what. See, that doesn't mean all the unsafe states are deadlocks, but all the deadlocks are the unsafe states. See, that is very clear. As long as a safe state is safe, the operating system can avoid unsafe or deadlock states. In unsafe mode, the operating system cannot prevent a process from requesting resources such that deadlock occurs. The behavior of the process controls the unsafe states. See, this is what the idea of the safe and unsafe and deadlock state. Now let us go with what are the approaches which we can use for the avoidance of the deadlock, that is the avoidance algorithms. See, there are two aspects. One is the resource allocation graph algorithm and one more is the bankers algorithms. The resource allocation graph algorithm is especially useful for the single instance of resource type. When we have a number of resources having each and every having single instance, you can use this, but it doesn't work for the multiple instance of a resource type. At that time we have to use the bankers algorithms. Now let us go with the resource allocation graph scheme or graph idea. See, we already know that the resource allocation graph, it has two edges, nothing but their request edge and assignment edges. Request edge is always directed from process to resources or instance of resource type, and assignment is always allocated or is always directed to the uh, um, uh, resource to the process. See, let us see. We add one more edge called claim edge. A claim edge is nothing but Pi to Rj is indicates the process Pi may request resource Rj represented by a dashed line. Usually it is represented by a dashed line. This edge resembles a request edge in direction but is represented by a dashed line. When process Pi requests the resource Rj, the claim edge Pi to Rj is converted to request edge. Similarly, when the resource Rj is released by Pi, the assignment edge Rj to Pi is reconverted to claim edge Pi to Rj. See, this is what conversion between these two. We note that the resources must be claimed a priori in the system. That is, before process Pi starts executing, all its claim edges must already appear in the resource allocation graph. We can relax this condition by allowing claim edge Pi claims Rj to be added to graph only if all edges associated with the process are claims. See, here uh, of course, that is very important, so that whatever the claims, they should be satisfied such that there is no circular weight happens. Suppose that Pi request resource Rj. The request can be granted only if converting request Pi to Rj to an assignment edge Rj to Pi does not result in a formation of cycle in the resource allocation graph. It is very important. The basic idea is that whenever a claim edge is going to be converted into request edge, there should not be any cycle formation in the graph. If it is forming, then there is a possibility of deadlock to happen. See, of course, an algorithm for the detecting cycle in this graph requires of order of n square operations, where n is the number of processes in the system. If no cycle exists, then the allocation of resource will leave the system in the safe state. If a cycle is found, then it cannot be allocated because it will enter to unsafe state, where then it has to wait. Therefore, the process Pi will have to wait for its request to be satisfied. See, this is about the resource allocation graph algorithm for the deadlock avoidance. Now let us go with the banker's algorithm. What is a banker algorithm? Banker algorithm is nothing but basically based on a banking system, where the bank ensures that the bank never allocates its available cash, so that it cannot satisfy the needs of all its customers. That is the basic idea of banker's algorithm, and it is best suitable for the multiple instance systems with the multiple instance of each resource type. But the resource allocation graph doesn't even work with the systems with the multiple allocation, multiple resource types. The deadlock, of course, deadlock avoidance algorithm that we see is applicable to a system where we have multiple instances of each resource type. See, of course, here each process must declare its maximum resources in the beginning itself. This is what the requirement. Yes. Of course, when a new process enters a system, it must declare the maximum number of instances of each resource type it may need. This number may exceed the total number of resources in the system. When a user requests resources that will set of resources, our system must determine whether allocation of these system will live in the safe mode or unsafe mode. If it will, then resources can be allocated, otherwise the process has to wait. Yes, it has a number of data structures requires, n number of process and m number of the resources types. There is a data structure called available, which is of length vector m, and of course there is number of available resources you can even think of. If available of j equal k means there are k instance of the jth resource type rj available. Max is n into m matrix. If max of I comma j is equal to k, if max of I comma j is equal to k, then process pi may request at most k instances of resource type rj. Next, the allocation matrix n into m matrix. If allocation I comma j equal to k, if allocation I comma j is equal to k, then pi is currently allocated to k instance of rj. That is the meaning of that. And the needed resources, again it is n into m matrix. If need of I comma j equal to k, then pi may need k more instance to complete its task. See, that is need of ij is equal to max of ij minus allocation of ij. See, this is what the different data structures we should use in the banker's algorithm. And now let us go the safety algorithm to check whether the system is safe or can be described. It can even whether it is safe or not. Let us go with the safety algorithm. Let work and finish with the vectors of length m and n respectively. Initialize work as available and finish of I means false for means nothing finished. I is a process, that is it. Find an I such that finish of I is equal to false and need of I is less than or equal to work. If no such I exists, go to step 4. Here, of course, then nothing is finished and need is required less than work. If finish of I is equal to true for all I, then system is in safe state. Otherwise, we have to do work equal to work plus allocation of I, finish of I is equal to true, and go to step 2. You continue, that's it. It is finished and then you continue. See, this is what the safety algorithm what we can have. Next, as well as we can have a resource request algorithm. Let request be the request vectors for the process, and if r of I of j equal to k, then process pi wants k instances of resource type rj. When a request process is made, process the following actions are taken. If request of I less than need of I, go to step 2. Otherwise, rise in another condition since process has exceeded the maximum claim. If request is I less than available, go to step 3. Otherwise, pi must wait. This is what we can even go with like that. Then yes, you can have make a system to pretend to have the allocated requested resources to pi. Make available equal to available minus request j. Allocation I is equal to allocation I plus request I. Need I is equal to need I minus request I. In this way, we can have a resource request algorithm to manage the deadlock avoidance. See, these are the different aspects.